All right, hello. Thanks, everyone. My name's Adrian Rehm, and I'm from Guelph, Ontario, so not far down the 401 from here. And I started with Metal Earth in 2017, actually, when it just first started. I was on the Noranda transect and did my thesis on the Pontiac subprovince there. And now I'm doing a PhD on the other side of the Superior, looking at the Quetico metasedimentary belt. And so I'm also part of the gold fluid window that we've been talking about for the last couple talks. And my study is following a similar approach to what Isaac described, looking at the tectonometamorphic history of the Quetico and then trying to see what the impact of dehydration or the role of dehydration had in the gold mobility. So this is also basically a collaborative project between Laurentian and Laval, as Antoine mentioned. And so really I'm not going to go too much into the introduction for the metamorphic dehydration model or the research objectives, because this was covered pretty well in the last couple talks. I'll talk a little bit about the geologic setting, but the main thing I want to do is present as many results as I can for you, and to help you come up with some discussion points and implications that we can talk about later. And so the idea is to really go from kind of the basin scale, the most regional that we can go so we did bedrock compilation maps and involving aeromagnetic interpretations, going down to the outcrop scale with isograd mapping and structural mapping, and then down to the thin section scale. Spent a lot of time in doing picturography, and then going into some of the micro and analytical results there. And then, of course, I'll include a little bit of thermodynamic modeling, not that much. Yeah, so two main objectives, overarching objectives for my thesis. It's really to try and get an understanding of the geodynamic setting of the Quetico. Isaac pointed out the kind of the debate right now in the geodynamic setting of these basins, so I won't go over that again. But really, the approach is to determine what are the metamorphic gradients in the Quetico and characterize those PT paths, because that gives us a lot of information on post-depositional geodynamics. And then with the metamorphic record, we can look at the crustal architecture, and the deformation history, of course, is going to go along with that. And then we can go from that framework into testing this metamorphic devolatilization model. And for this talk, I'm really mostly going to be talking about the timing of the deformation events relative to metamorphism. So the QS, the Quetico subprovince, is really a major feature of the Superior, Western Superior province. It covers almost 1,200 kilometers from the United States all the way to the Kapuskasing structural zone. And it's one of the, I guess, 6 metasedimentary subprovinces in the Superior. What makes Quetico unique, especially from the Pontiac, is that you have both the north and southern margins of this subprovince are very well preserved, whereas in the Pontiac it's completely cut off by the Grenville. So we have the Wabigoon to the north and Marmion terrain, just a bit older, and then the Wawa, I guess, Abitibi terrain to the south. And this study also includes the transitional boundary areas. So we're talking about the Beardmore-Geraldton belt up in the eastern Wabigoon, and some of its analogs in the southern part, which I'll talk about. And the symmetrical metamorphic zoning is really what characterizes all of these sedimentary basins, where you go from really low-grade green schist to the margins, and then melt zone granulites into the center. In terms of the timing of sedimentary and supercrustal sequences, we have the sedimentary rocks were deposited around 2.7 billion years. And these are basically interpreted mostly as turbiditic wackies. And we have basically minor volcanic rocks, which include the Beardmore-Geraldton belt and such rocks, which are basically mostly mafic foliates. And from our mapping and what we've seen in the field is we've determined that it's pretty most sedimentary, the relationship between these volcanic rocks and the sediments. And so I'll talk maybe a bit about this later, but maybe not too much. The intrusive rocks are very diverse in the Quetico. So you can see lots of sanucatoid magmatism, especially at the margins of the subprovince. We also have calc-alkaline mafic to ultramafic intrusions, which are up in the Adicocan area. We have syenites and carbonatites, and of course the S-type granites. But the main ones that I'll be talking about are the ones in the 2695 to 2670. So the first results I'll show are from the transect mapping. We did about 15 north to south trending transects through Adicocan area all the way to Geraldton and Manitouwadge, actually. And so we mapped about 600 stations, outcrop stations, collecting samples, mapping the mineral assemblages that we can see, especially the isograds, and getting structural data from that. And then we used historical maps of that whole area, as well as the aeromagnetic imagery, to produce a new geologic map of the Quetico, which I showed on the last two slides, actually. So this zooms in on the Geraldton area and shows the sequence of metamorphic zones, or isograds, which just represents the first appearance of these index metamorphic minerals as we go from north to south in this case. And so I'll just go through them one by one. We have the chlorite zone, which is at the lowest grades in the margins. And we have a biotite comes in shortly after we go into the Quetico, or in this case, we're actually still in the Beardmore-Geraldton belt. And for certain lithologies that are calcic, we get hornblende appearing at that time, garnets, and then storolite. And storolite coincides with the occurrence of andalusite, very commonly occur together if you have the right bulk composition. And then chlorite is essentially gone by that point. And then the next sequence is cordierite and silmonite, which are typically very close together, these isograds. And then we have the in situ melt that occurs after that. And then the OPX orthopyroxene zone isn't shown on this map, and that really is only restricted to the Manitouwadge area. It's not really found especially in the western part. In terms of the structural geology, I'll point out a couple of key points here. That the younging direction is typically towards the margins of the basin. So in the northern part, most of especially in the low grades, we see that the younging direction is consistently northward. In the southern part, it's to the south where we can see it. And then when we get into the garnet and storolite zone, this is kind of the area where we typically start seeing reversals in the younging direction. And so this is associated with this D1 isoclinal folding. And really this younging reversal can occur within like 100 meters or less. So these are they're not regionally mappable isoclinal folds. They're more localized. And what's interesting is that they don't really develop a strong foliation that you can see pervasively in the rock. Really, it's mostly inferred from porphyroblasts, which I'll talk about in a bit. The main regional fabric is the D2 subvertical foliation, and that's associated with open to tight upright folds, which are mapped here and there. And there's a lineation, mineral lineation and fold axes that are typically in this area, in the central part of the Quetico. It's very shallow tipping, like 20 to 30 degrees to the east. Interestingly enough, it seems like it gets steeper at the margin. So in the low grade zones, you get a steepening of this plunge, and in fact, it starts plunging in the other direction to the west in the Geraldton area. And then this is finally, we have a late dextral strike slip event, which is well recorded by the Quetico fault. And we see this develops locally in shears, but also it's quite a dominant fabric within the migmatite zone. So this is an example of a very small scale F1 isoclinal fold. and there's no associated cleavage with that. Potentially, soft sediment deformation might have produced this. And then this is an example of the D2 deformation, where these quarterite blasts are lineated parallel to the fold axis, and then you have an S3 crenulation, which just kind of appears to be deforming those blasts after. Okay, so one of the main things we want to do with this bedrock compilation is to look at map patterns. And so I'm going to list a couple of these observations, or more interpretations, I guess, of the data. And so it's not really shown on this here, but we have a symmetrical zoning of the lithologies. So it means at the margins of the subprovince, we have more mafics, we have more volcanic rocks. Talk a bit more about the protoliths in a second. But the intrusion style also varies. So at the margins, we get these kind of stalk-like intrusions. You can see them on the mag imagery. They occur as these lobate bodies. Whereas once you get into the central part, the same rocks really become dikes. They're elongated, parallel to the main foliation. So it's definitely a different style. The isograds, well, first the intrusions appear to be deformed on the magnetic imagery by this late faulting. I've attributed this to D3, where typically a D3 you can see an east-west main shear zone here, and then you have, I guess, these smaller faults that are coming off of that shear zone. Kind of resembles a C prime texture that we typically see in those shear zones. So that kind of C prime geometry is really what characterizes what the Quetico looks like now. So it's really the last deformation event that's showing the current structure at a regional scale. And the last thing I'll show is that from our mapping of the isograds in this area especially, we see that there's a bit of a difference in the shape of the isograds, where the garnet and biotite typically follow the margins of the subprovince a little bit better, and will diverge from the storolite, cordierite, silmonite, and melt isograds, which all appear to be more parallel to the contact with the migmatites. So it's a bit subtle here, but it does tell us that we might be dealing with two different gradients, and that's exactly what I'll talk about. So just quickly, the main protoliths are semi-pelites to pelites. With the pelitic layers contain variable porphyroblasts depending on where we are in the subprovince. We also have these calc-pelites, calcareous semi-pelites, which appear to have clasts of carbonate material, and then at slightly higher grades you'll get amphiboles, porphyroblasts growing from these. And then these mafic tholeiitic basalts are also interlayered within the sequence. Okay, so just the petrography, we did a full analysis on 180 samples, including estimates on modal proportions and textural relationships. I'm only going to quickly talk on the whole rock just to help with the classification of these protoliths. And then we used mostly optical microscopy and SEM and micro-XRF to look at the textures mostly. So for classification, the most common rock is the semi-pelite, of course. But what we found is that, especially at low grades, it's kind of difficult to distinguish what a semi-pelite and a pelite is, because there's no index minerals at those grades. So we found that a cutoff of about 50% of quartz plus plage really distinguishes those porphyroblast-bearing assemblages from the non-porphyroblast-bearing assemblages. And then we can see that you add a bit of calcium to the sample, and we plot along this calcareous semi-pelite field. And this is really the first step of trying to separate out the protoliths, compartmentalize these protoliths in order to look at what their different impacts are on the fluid generation, et cetera, which is coming a bit later. And just this is quickly just to show that this classification scheme is also shown within the major element chemistry. So it's really dominated by the aluminum, potassium, and calcium content in the rock. Seems to be controlling the mineral assemblages very strongly, and generally very sodic compositions. Plage is generally more common than quartz. For the distribution of protoliths, what we see, I touched on this, it's zoned at the margins, the lithologies. So what we can actually compartmentalize the Quetico into its crustal crustal levels, if you want to use isograds as crustal levels, with the chlorite and garnet zone, which would be the highest levels, and then the storolite to OPX zones, which would be deeper crustal levels. And you can see there's a difference in the distribution of the protoliths. And this is just from mapping estimates, but this is the actual sample suite. So that kind of takes away the eyeballing that goes into that, but of course there is a bit of sample bias that goes into the actual sampling. This sample suite includes both mine and Diogo's samples, so we have a bit of different goals in our sampling. Like I sampled more of the pelites, so it's definitely going to be a bit skewed towards the porphyroblast bearing pelites. But overall, it kind of validates that it's, I guess, a pretty good estimate, as best we can do at this point, I think. Okay, so now on to more of the textural relationships. And one of the key observations that or interpretations that we're making from the Quetico is that we have polymetamorphism. And so really this is one sample of a pelite within the chloride zone, so very close to the Atikokan boundary there. And we have these relict cordierite porphyroblasts, which display kind of a subtle S1 foliation within these lobate cordierite porphyroblasts. And they're almost entirely pseudomorphed by muscovite and chlorite. And really you have to go in very, very, very small to get to any fresh cordierite left. So it really indicates that you had a cordierite and with, I guess, biotite inclusions there that has been overprinted by the chlorite muscovite assemblages, which is the regional isogradic assemblage, which also defines the main foliation, which in this case, S2. This is similar textures just at within the garnet zone here, and then within the storolite and andesite zone here. The garnet is a bit of a key player here because that textural relationship is sometimes ambiguous. But for the most part, we interpret that garnet is late to post S2 and after these cordierite and andesite porphyroblasts. And this is kind of shown by the overprinting of these euhedral garnets over this S2 foliation, which is that S2 is deflected by this porphyroblast here. So that's kind of the rationale there. So, and then we assume that we interpret that it's polymetamorphic here because we see the chlorite to garnet transition, which is something that you typically wouldn't get if you're just increasing pressure, a single path of increasing pressure. So. Now the monazite petrochronology was a big part of this. I did 4 samples from each of the storolite, cordierite, sillimanite, and melt zones. We did uranium lead isotopes, of course, as well as trace elements. This was done on the triple quadrupole at Laurentian in the past year, and 15 micron ablation spots tried to do mostly thin sections, and then if we didn't have enough, we would use the grain mounts as well. So there's 2 dates that I'll present on this slide is the 2660 age, 2660 plus or minus 4, and 2662 plus or minus 6. These are within the storolite and cordierite zones. And I'll just mention that all of these have a single population, these samples. So we're not dealing with polymetamorphism or record of different metamorphic monazites within the same sample. I'll mention here that the monazites are evenly distributed in the matrix and don't show any preferred orientation, which is going to be in contrast to a bit later. And it's included in both the storolite and cordierite porphyroblasts here. And this relationship of cordierite to the L2 fold axis, where we see that they're essentially cigar-shaped, parallel to this fold axis, kind of tells us that these are, we interpret it that it's pre the main deformation, pre-D2. And so this would be a prograde M1 assemblage. And this is kind of, we expect the monazite to form in a prograde sequence where you break down allanite or potentially apatite at around the garnet to storolite transition, which is very consistent with our data. We didn't find any garnet or any monazite in the garnet zone. This is a supersolidus sample, so this is a paleosome where you have a little bit of partial melting. And again, we see that the monazites are a bit coarser in this case. I actually use a 25 micron spot size. So it makes sense that we go from a smaller spot or smaller monazites to bigger monazites as we increase temperature and start melting. So the interpretation is that this is part of the same prograde path as the previous sample, and we're getting high enough temperatures to start melting at 2677. And then this sample is quite a bit different than the other ones, where we're clearly seeing that the monazites are elongated in this case. They show a fabric, and indeed they're parallel to the S2 fabric defined by the main biotite foliation. So these monazites are parallel here, and they're actually included within this Andalusite porphyroblast. And this Andalusite porphyroblast is a bit different than the first one I showed, where it actually shows a rotated inclusion trail, which is consistent or continuous with the external foliation. So we interpret that this is a syn S2 porphyroblast, as well as the monazite is dating that S2 fabric. And so this is 2660, about 20 million years younger than the M1 monazites. Okay, so I'm just going to show one pseudo section here so we can kind of discuss what kind of pressure and temperature conditions we're at. Use the MNCKF mash toe system, and as Isaac mentioned, we corrected for apatite and sulfur or sulfides, in this case pyrrhotite. And so really the difference between mine and Isaac's work here is that the PT vectors that we're estimating is really based on the progression of mineral assemblages, the sequence of mineral assemblages that we see in the textures, rather than this detailed isopleth and isomode work that Isaac showed. So it's a bit of a different approach here. And so this is the pseudo section here. The kind of the main stability fields I want to highlight are the garnet in field here, which is really restricted to higher pressures and temperatures. The storolite field is this one, comes down to slightly lower pressures at around 550, which is where we have this inferred PT vector. And then the cordierite, this is the cordierite in zone here, which is restricted to generally lower pressures and higher temperatures. So we have a pretty good estimate for this G1, this gradient, this vector here, which goes through the storolite, andalusite, cordierite, and sillimanite fields into the melt zone. So this reflects really well what we see in the central parts of the Quetico. When we try and go to the exterior of the Quetico, the marginal parts, it doesn't really fit along this gradient at all. In fact, we need to increase the pressure quite a bit in order to get garnet before storolite at all. And so here we can't say much about the orientation of this gradient maybe, but what we can say is that it's pretty much restricted to higher than 5 kilobars. So the 8 kilobar that Isaac presented earlier is consistent with that. Yeah, I think I talked enough. Right, so the discussion here, we're going to talk about the first metamorphic event. So we see that the monazites are coeval with the sanucatoids in general, which are in 2690 to 2670, as I mentioned. So this kind of, we're in a sort of magmatic high we need to be in an extensional environment to get these kind of features. The high temperature gradient, the synucleoids, this is all indicative of an extensional setting. But this raises the question as to why do we get isoclinal folding in an extensional environment? So this is kind of a bit of a problem right now. We see something that we have to consider, and as to what's the mechanism for developing these types of folds in this environment. Maybe we have to invoke diapirism or something like that. And the other point that I want to mention is that we don't see the development of these major vertical fabrics or structures. And one thing that maybe we haven't mentioned earlier in this gold fluid window project is that the timing of deformation and the formation of major fabrics coeval with metamorphism is really what's required to bring these fluids out of the rock and into the higher crustal levels. So if we don't have a penetrative vertical fabric, does that mean that we can't be mobilizing fluids into higher crustal temperatures? I don't know if we have that answer. Or the other option is maybe that it's actually concentrating fluids at certain crustal levels, which could then be mobilized during M2, which I'll talk about here. So the M2 is interesting because this appears to be coeval with, or two gradients characterize it. So we saw that the marginal and central parts of this Quetico have not only different gradients, but different styles of magmatism, different styles of the protoliths versus the center. So this kind of goes into what Isaac was describing and Antoine was describing, that we have this kind of indication of a crustal overturn where the center is hot and is rising, and we have some burial of things at the margins. And so this M2 D2 event is really coeval with our subvertical structures. And really the best estimate that we have for dating the development of those structures is the age of 2660. So is this really the timing of the fluid release migration? Because again, that's when we get our vertical structures. It's entirely possible, but if we consider like the classic model for metamorphic devolatilization in a Barovian type sequence, this would preclude a metamorphic source for deposits that are earlier than 2660, if we adopt that model. But then again, there could also be the impact of having two metamorphic events might actually increase the impact that the second metamorphic event has by concentrating fluids in certain layers. But this is all a bit of a discussion at this point. So main conclusions here that we see that again, the protoliths and the gradients are different at the centers and its margins. The D1 flatline isoclinal folding appears to have occurred in some sort of extensional setting, early extensional setting. We have prograde ages at about 2660 to 2675, and then an M2A to 2660 million years. And so again, I mentioned this, the lack of vertical structures before M2 might preclude a metamorphic fluid source for deposits, nearby deposits that are older than 2660. The next steps are going to be doing some of this detailed lutetium, hafnium, garnet petrochronology by not just looking at the gradients, but we want to see the shape of the PTT paths and try and quantify that a little bit better, and maybe even talk about the rate of these metamorphic events. And then we're going to try and incorporate carbon, hydrogen, and sulfur fluid into our phase equilibrium model, and to look at the pulses of fluid and ligand release, and look at the different protolith contributions that we have to metamorphic devolatilization. So, thank you.